All right, so this problem says scouts at a camp shake the rope on a bridge and they've just crossed and observed the wave crests to be 8 meters apart. So 8 meters is roughly half the width of this room. If they shake the bridge twice per second, what is the propagation speed of the wave? Okay, so here's the bridge. Okay, and this distance is 8 meters, and that is the wavelength of the wave that's traveling on the bridge. Okay, and they're shaking the bridge twice per second, so the frequency is 2 hertz. Okay, hertz is 1/2. Okay. So the problem is fairly simple, and they ask you what is the propagation speed of the wave. So what is the speed at which this wave travels? In reality, if you do this, what happens is you have a wave traveling like that, and at the end of the bridge it will be reflected, and what you'll do is you'll set up standing waves of what you'll end up doing, just like a musical instrument. Okay. But anyway, so the speed of the wave is frequency times wavelength, and so it's 2 hertz times 8 meters, 16 meters per second. Yep. 10 meters is about 25 miles an hour, so this is about 40 miles an hour. Okay. So this problem says, what is the wavelength of an earthquake that shakes you with a frequency of 10 hertz, so 10 oscillations per second, and gets to another city 84 kilometers away in 12 seconds? Okay. So the speed of the wave is 84 kilometers divided by 12 seconds. Okay, this is 7 kilometers per second. And earthquake waves, they're both longitudinal and transverse waves, because in solids you can have transverse waves, and it turns out that these are called P waves, or primary waves, because they arrive first. The speed of the transverse waves is about 4 kilometers a second. Okay, and these happen to be longitudinal waves, but anyway, they're primary waves. So this is 7,000 a kilometer. That's a prefix for 10 to the power 3. So this is 7,000 meters per second. That's the speed of the wave. Okay. And the frequency is speed is frequency times wavelength. So the wavelength of the wave is v divided by frequency. It's 7,000 meters per second divided by 10 hertz. Hertz is 1/seconds. (700 meters). So 700 meters is roughly from Clyde Morris to Nova. Okay. So that's maybe a little more than that. Okay, this problem says your ear is capable of differentiating sounds that arrive at each ear only 0.34 milliseconds apart. So if you hear a sound here on your left ear, if the sound arrives at the right ear in less than 0.34 milliseconds, you won't be able to tell if they came at the same time or they came apart. Okay. So for instance, here in air, If something is on the sounds on the left, that delay is enough for you to tell. You can close your eyes, that you can tell that the sound source is coming from the left. Okay, so from time delay you can tell where the source is coming. If the sound is coming from directly ahead, they reach the ear at the same time, and so you know it's either in the front or the back. Okay. Now if you went underwater, if the sound plays from the left, underwater the speed of sound is 5 times greater. So you can't tell which direction the sound is coming from. Okay? So manatees have that problem. Well, they can't swim fast enough anyway, but that's one of the problems. Yeah. So if you're underwater and a boat is chasing you, well, you have no luck. But anyway, your ear is capable of differentiating sound that arrive at each ear just 0.34 milliseconds apart, which is useful in determining where low frequency sound is originating from. You'll see low frequency sound. So what this means is, so let's say if it was 100 hertz frequency sound, the wavelength would be, V is 340 meters per second. So the wavelength would be 3.4 meters. Okay. And if the wavelength of the sound is bigger than the size of your head, it's like your head is not even there, it'll just go around it. Okay. So for low frequency sounds, this time difference is how you locate the direction of the source. Okay? So this is useful in determining how where low frequency sound is originating. Suppose a low frequency sound source is placed to the right of a person whose ears are approximately 18 centimeters apart, and the speed of sound is 340 meters per second. How long is the interval between the sound arriving at the right ear and the sound at the left ear? Okay, so well, here's your head there. Okay, so there's the sound arriving, and this distance is 18 centimeters. So the time to traverse that distance is that distance divided by, okay, so the time difference is that 18 centimeters is 0.18 meters divided by 340 meters per second. So the time difference between the so as long as the speed of sound is that, which is the speed of sound in air, you can easily tell the direction of the source. Okay. Now you see, if you increase the speed of the sound in a medium, so for instance in water, the speed of sound is 5 times greater, this time difference would become 5 times less, which would become 0.1 milliseconds. So underwater you couldn't tell where the sound is coming from. So that's what part B is. Assume the same person is scuba diving and a low frequency sound source was to the right of the scuba diver. How long is the interval between it? The speed of sound in water is 1500 meters per second. See, roughly 5 times as much. So delta T would be D over V equal to, again, 0.18 meters divided by 1500 meters per second. 0.12 milliseconds. Okay. So underwater, you lose all sense of direction for the sound. Okay. So that's the significance underwater. Okay. You can't tell what direction the source is coming. Okay, this problem says a pulse can be described as a single wave disturbance that moves through a medium. Consider a pulse that is defined at time t equal to 0. So there's this pulse centered at x equal to 0 meters. The pulse moves with a velocity 3 meters per second in the positive x direction. So they ask you, what is the amplitude of the pulse? Okay, so the amplitude of the pulse, if you plot this pulse looks almost like a bell curve, except that it doesn't decay as fast. Okay. So that's how the pulse looks like. The amplitude, that's the amplitude of the pulse, the maximum value. And you see that happens at x equal to 0, and that would be 6 by 2, 3 meters. So this pulse is 3 meters. Okay. And again, like this, 3 meters is almost, well, 2/3 of the way to the roof. Okay. So this could be a water wave, a pulse in the ocean that's coming near the beach. Okay. And now what you want to do is, what is the equation of the pulse as a function of time? So now you want to make it travel to the right at 3 meters per second. How do you make a pulse travel to the right? What? So here's how you make the pulse travel to the right. You replace x by x minus vt. Okay. And if you wanted to make it travel to the left, what would you do? Plus vt. So here is the pulse traveling to the right. Where is the pulse centered at t equal to 5 seconds? So at t equal to 5 seconds, this would be 15 meters, and the pulse would be okay, so the center, the peak would be at 15 meters. That's where the pulse would be. Okay. Okay, so there's a similar pulse. Okay. Again, this is very similar to this. This is a bell curve. Again, and you can see that this pulse is traveling to the right at 2 meters per second. Okay, wherever x got replaced by x minus vt, the v is that's the speed of the pulse, and the negative sign just telling you that it's traveling to the right. Okay. So use a spreadsheet to plot the pulse as the height of so what is the height of the pulse for okay, so the amplitude is 1, so the height at x equal to 0 at t equal to 0 and x equal to 0, this would be 0, and so e to the power of 0 is 1. Okay, so this pulse, Again, this is a bell curve. Okay. So it's just like that, the previous pulse, and the amplitude is 1. So y, this is at t equal to 0. And so this is at t equal to 0 and t equal to 3. T equal to 3 seconds, it'll be 2 times 3, 6 seconds, and this will be centered around 6 meters. This will be 6 meters. Yep. So that's how the pulse travels. You guys understand? Okay. All right, in this problem, a wave is modeled with the function that find the amplitude. So we'll want to find various wave parameters. So here is the pulse yxt equal to a cosine kx minus omega t plus phi. So that's the standard form of the wave. Either you can use a sine or a cosine function. Okay, this is the amplitude, this is the wave number, this is the angular frequency, and this is the phase. Okay, so now given your wave function, you can identify all those quantities. Okay, so your wave function is 0.25 meters cosine 0.3x minus 0.9 t plus pi over 3. Okay, so the amplitude is 0.25 meters. The wave number is 0.3, and everything is SI units, so it's meter inverse. Okay, remember the units, you find out the units as follows. What are the dimensions of this guy? What are the units of this guy? Do you guys know? Well, first thing, let's answer this. What is this thing called? That's called the phase, and it's dimensionless. Okay, so if this is in meters, that'll be in inverse meters. This is in seconds, that'll be inverse seconds. And this is in radians, which is dimensionless. Okay, so wave number is 1 over meters. Okay. Angular frequency, omega is 0.9 radians per second. Okay, so we will write it as radians per second, except that radians is just a label. Okay. Wave speed is omega by k, which is also equal to frequency times lambda, but since we have omega and k, we'll write it in those terms. Omega is 0.9 and k is 0.3, 1 over meters, so wave speed is 3 meters per second. And then we have the wave speed phase shift. This is the phase shift. Okay, that's the phase at x equal to 0 and t equal to 0. The phase shift, wavelength, and the period of the wave. Okay, so we'll find the wavelength we'll get from this number, period we'll get from this number. Okay, so there is the phase shift. The phase shift is pi by 3, and f is wavelength, so k is equal to 2 pi by lambda. Lambda is equal to 2 pi over k. 2 pi over k is 0.3 meters. And so And period omega is 2 pi f equal to 2 pi over t. Seconds. All right, so the point of this problem was, see, this representation of the wave contains all that information. Okay, so that's what we wanted to show you. Right, so in this problem, a piano wire has a linear mass density of 5 times 10 to the minus 3 kg per meters. So that's 5 grams. Under what tension must the string be kept to produce a wave with a wave speed of 500 meters per second? Okay, so the wave speed on a string under tension is given by that. And they're asking us to find the tension. What must be the tension to produce that speed? Okay, so V squared times mu is the tension. So mu is V is 500 meters per second. And so that's, you get 10 to the minus 4, so it'll be 50 times that. And it's tension, so the units will be newtons. Oh no, that's a 5 square, so that'll be 250. So that's the tension on the string. So this is a little over middle C. Okay, so those wires in a piano are under this kind of tension. This is twice the weight of one of us. So those wires are wound around metal frames. And back in the old days, it used to be around wood frames, and then if the wood snapped, that could cause some damage. So once the metal frame started being used, they became a lot safer. All right, so 2 strings are attached between 2 poles separated by a distance of 2 meters as shown. Both strings have a linear density, so their linear densities are the same. The tension in one is 600 newtons and the tension in 2 is 700 newtons. How much time passes before the pulse pass one another? Okay, so we'll call this 1, this 2. So let's calculate so the velocity is tension divided by mu. So V1 is 600 newtons is the tension, and mu1 is 0.0025 kg per meter. Okay, so this will be 25 times 10 to the minus 4. The 10 to the minus 4 comes to the top, and then square root of that would be 10 to the 2. So 600 divided by 25. So V1 is so 489.9 meters per second. Similarly, V2 is 700 and this will work out too. $700 divided by 20. So 529.2 meters per second. So you see, the greater the tension for the same mu, the greater the speed. So when you increase the tension from 600 to 700 newtons, the speed went from 490 to 530 meters per second. Yeah. So transverse pulses are generated simultaneously on opposite ends. So you generate a pulse on this end and this end simultaneously. And the question is, at what time will they meet? Okay. So let's say this travels a distance of x before they meet. So this guy has traveled how much? 2 minus x. Okay. So x equal to v1 times t, and 2 minus x equal to v2 times t. Okay. So 2 minus v1 times t equal to v2 times t. What we've done is we've taken this and substituted there. So 2 equal to v1 plus v2 times t. I brought this over there. So t, they will meet after 2 meters divided by v1 plus v2. So they will meet up after 1.96 milliseconds. Okay. Okay, this problem says the note E4 is played on the piano and has a frequency of 394 hertz. If the linear mass density of the string is that, and the string is under tension of 1,000 newtons. See, all these tensions are up in the piano strings are about twice your weight. What is the speed of the wave on the string and the wavelength of the wave? Okay, so the speed is given by tension divided by mu. So here I can write this as 10 to the minus 3, that comes to the top, and then this becomes 10 to the 6, and then square root of that would be 10 to the 3. So it would be 10 to the 3 again, and meters per second divided by square root of 12. Okay, so about 289 meters per second. And then the wavelength would be, so the wavelength is V over the frequency. Hertz is 1 over second, so okay, so that's the wavelength of the wave. So this says a string of length 5 meters and mass 90 grams is held under tension of 100 newtons. A wave travels down the string, and there's the equation of the string. What is the power over one wavelength? Okay, so well, okay, so this should be really what is the energy over one wavelength. Okay, so here's a formula for the power. Okay, so here's the power formula for the power. That's how much energy travels per second across a point. Okay, so to get the energy per wavelength, we'll do power times time. So 1/2 mu v omega square a square. Okay. Power is energy over time. So the energy in one wavelength is the power times the time it takes for the energy one wavelength to pass you. And the time it takes for one wavelength to pass you is the period of the wave. Okay. So all this information is contained in here. Okay, so let's first find the period. There's omega. Okay, so there should be a t there. That's so there's a couple of typos. All right, so omega is 2 pi over t over, and omega is 1170. Okay. Okay, so the period of this wave is 5.37 milliseconds. Okay. Let's calculate mu. Mu is mass per unit length, and mass is 90 grams, which is that many kilograms for 5 meters. Okay. So this is 18 into 10 minus 3 kgs per meter. That is mu. We need we have mu. We need the wave velocity. The wave velocity is omega by k. So there's the wave velocity. Okay, so we have that, we have that, we have this, and we have that. There's the amplitude, and we have the period. Okay, so now we have everything to calculate the energy that is contained in one wavelength, and that energy is traveling down the string. Okay. So E is power is 1/2 mu v omega square a square times t. Mu is 18 times 10 to the minus 3 kg per meter. V is 2009-25.3 meters per second. Omega is there's omega 1170, and amplitude was 0.1 meter square, and then the amplitude is 0.01 meters. And the period is 5.37 milliseconds. 5.37 milliseconds. Okay. All right, let's take care of powers of 10. Here's 10 minus 3, 10 minus 6, and we'll make that 2.95 So that's 10 minus 3, then that's 10 to the 6, so 10 to the plus 3, and this is 10 minus 4, so you get 10 minus 1. So this is equal to 0.5 times 10 minus 1. That's assuming if I did it all right. Okay, so 10 minus 4, 10 minus 7, 10 minus 10, 7, 10 minus 7, and 10 minus 1. Okay, yep. Into 18 into 2.93 into 1.17 square into 5.37. And what are the units? Joules. Yeah. That's the SI unit for energy. So about 20 joules. So what we have found is, you saw that when you send a wave down a medium, what the disturbance is carrying is energy. What is being carried is energy. And what you're saying is, this much of the wave is carrying 20 joules of energy. Okay, and 20 joules is 1 kg. So if you think of this 20 joules as, so energy, so think, here's a good way to picture this. You take 1 kg, and this is 10 meters, 1 times 10 times 2 meters. So if you take your 1 liter water bottle, is that a liter bottle? That's half a liter. Okay, so hold it up. So 20 joules would be, you take that bottle of water and drop it from the roof to the ceiling. That's how much energy that is. That's a bit of energy. Okay. All right, they say ultrasound of intensity 150 watt per meter square is produced by the rectangular head of a medical imaging device measuring 3 centimeters by 5 centimeters. What is the power output? So power, so power is intensity divided by area. Okay. Intensity is the energy. No. Intensity is power times area. Okay. Intensity is the energy emitted per second. Okay, intensity is the energy reaching you per second. Power is no. I'm mixing this up. Power is intensity times area. Okay, so intensity is energy per second per unit area, and intensity times area gives you power, energy per unit time. Okay. So yeah, okay, so the power is, intensity is 150 watts per meter square, and this is 3 by 5 centimeters. Centimeter square is 10 to the minus 4 meters square. Okay, so this is, that's 15. 15 times 15 is 225. So 225 times that into 10 to the minus 4 watts. Okay, so 0.225 watts. So the power of that ultrasonic device is that 3 centimeters by 5 centimeters. That's about 1 inch by 2 inches. Okay. So it's a fairly low power device.